Guys, welcome back to my channel. Keep calm and love math. This is part 3. In this session, I am going to do some problems related to we have discussed earlier problems on reflexive, symmetric, and transitive relations, equivalence relations, etc. I am going to solve the problems from the book A Class Book of Mathematics by XII. And so here the first question is, state true or false. 1. R equal to ordered pair A comma B such that A and B belongs to a set A and it is defined as A into B equal to 100 is an empty relation in the set A equal to X such that X belongs to N where X less than 10. So we are given a problem. We have to verify either this relation is an empty relation or not. So let's proceed. R is an empty relation. So and it is a binary relation. So R goes from A to A itself. Now the definition of empty relation is what? According to definition of empty relation, no element of this set is related to any element of this set. So let's see. Here R equal to in such that AB equal to 100. Now A means 1, 2, 3, 4, 5, 6, 7, 8, 9. Since X belongs to capital N, that means X is natural number and less than 10. The natural numbers less than 10 are 1, 2, 3, 4, 5, 6, 7, 8, 9. Now product of the two elements in the ordered pairs should be equal to 100. Since R goes from this set to this set, therefore we cannot find any pair AB such that A into B equal to 100. Here 1 into 1, 1 not equal to 100. Similar way, if we multiply 1 with the elements this, we cannot find 100. Similarly, 2, 3, 4, 5, 6, 7, 8, if we take all this, we cannot find 100. Now let's see, 9 into 9, 81, which is also not equal to 100. Therefore, we cannot find any pair in this relation. So this relation will be an empty relation. So this statement is true. So 1 is true. Now the second question is, R equal to ordered pair A comma B such that A plus B equal to 5 is an empty relation in the set of whole numbers. So we have to check either this relation is an empty relation in the set of whole numbers. So now the set of whole numbers, let the set of whole numbers be A. Then the set A contains the element as 0, 1, 2, 3 up to infinite. That means R goes from A to A. Now are there any pairs A comma B such that A plus B equal to 5 for the set of whole numbers? Yes, obviously we have. How? Here 2 plus 3 equal to 5, which is satisfied according to the equation. 1 plus 4 equal to 5, right? 3 plus 2 equal to 5, 4 plus 1 equal to 5, 5 plus 0 equal to 5, and similarly 0 plus 5 equal to 5 also. So the relation R A B such that A plus B equal to 5, it contains some elements which are 0, 5, 1, 4, 2, 3, 3, 2, 4, 1, 5, 0. So is the set R is empty? No, right? So this relation cannot be empty on this set of these whole numbers. So the given question is false, because in the question we are given that R is an empty relation. So the statement is false. Have you understood? I think you are getting it, right? Now come to the third question. Number 3. R equal to ordered pair A comma B such that A B belongs to a set A and modulus of A minus B is less than 5 is an universal relation in the set A equal to X such that X belongs to R, where minus 50 less than X less than 50. So we have to check whether R is an universal relation on the set A. Now, by the definition of universal relation, we have any element of A relates to each element of A, right? Which is the definition of universal relation. Now we see here R goes from the set A minus 50 less than X less than plus 50, and X belongs to R, that means real number. So can we say that A is an interval? The set A is in the form and A is the set in the form of an interval which is minus open interval minus 50 comma plus 50. So R goes from open interval minus 50 comma 50 goes to minus 50 comma plus 50. Now is there any pair AB to fulfill this condition? Let's see. Now if we take the number 5 and 1 which are belonging to this interval, modulus of 5 minus 1 means modulus of 4, and modulus of 4 means 4. 4 is less than 5. It satisfies the condition this. Similarly, minus 5 plus 1 equal to minus 4, but we have the modulus symbol, so the value will be plus 4, which is less than 5. This is also satisfied. But we have another pair, the numbers minus 50 and 50. Let's see whether this pair satisfies the condition modulus A minus B less than 5. Modulus of 50 minus bracket this number minus 50 equal to 50 minus goes plus, so modulus of 50 plus 50, and 50 plus 50 equals 100, but 100 is greater than 5. It is obvious, we know. So this pair contradicts the fact which we have given in the question. So if we have such type of question, then it is very important to check a counter example. Because it is very important. Here we can see this pair does not satisfy the condition. So this is a counter example of this question. So it contradicts the fact. Therefore, R cannot be an universal relation, because in the universal relation, each element of this set relates to each element of A. But we have a counter example. So this cannot be a universal relation. That's it. Have you got it? If you are not getting my point, then you can pause my video. Then you can repeat, and also you can take a screenshot of this. Now come to the next question, which is 4. R equal to ordered pair A, B such that A, B belongs to capital N means natural number and A plus B greater than 0 is an universal relation in N. We have to check whether this relation R is universal relation or not. Now you know about universal relation. So, and R is a binary relation. R goes from N to N. Now we know the sum of two natural numbers. The sum of two natural numbers is always greater than 0 because natural numbers start from 1, 2, 3 up to infinite. So the sum of two natural numbers always greater than 0. It is very obvious. And the condition is satisfied here. Therefore, this relation is an universal relation. So the statement 4 is definitely true. Now the last statement of the first question, which is R equal to AB such that AB belongs to a set A and A minus B equal to 2 is neither an empty relation nor a universal relation in the set A 0, 1, 2, 3, 4, 5. So this is the question. You have to verify whether R is an empty relation or universal, because we have to check either this statement is true or false. So this is a homework for you, and answer me in the comment section so that I can come to know whether are you learning from this video or not. So second question. Question number 2. State whether the following relations are reflexive, symmetric, and transitive. So the second question is, we are given some relations. We have to check either they are reflexive, symmetric, and transitive. Number 1 is R equal to ordered pair x, y such that xy belongs to a set A and it is given that y is divisible by x. The question is like, there is an ordered pair xy and the second element is divisible by the first element. It is given. Now R from A to A, no doubt. Now y is divisible by x, so the element of R will be 1, 1. Here 1 is divisible by 1, right? So R contains this element. Now 1, 2. 2 is divisible by 1. This is also right. Similarly, we have some pairs 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8. Since we have the elements 1, 2, 8. Now 2, 2 is also an element in R because 2 is divisible by 2. Similarly, 4 is divisible by 2. Similarly, we have some other terms. So you can see R is a relation containing all these elements. Now we have to check either this is reflexive, symmetric, or transitive. Now you know reflexive relation means the element is in the form AA. This is reflexive. Symmetric means when an element AB belongs to a relation, it implies BA also belongs. And third one is when we have two elements in a relation. Suppose these are AB and BC, then this should imply we have another element AC belonging to this relation. So let's see. Here 1 1, 2 2 and 3 3, 4 4, 5 5, 6 6, 7 7 and 8 8. All the elements in the form AA. For all elements in the set we have in R. Therefore, obviously R is reflexive, right? So R is reflexive. Now, to check whether R is symmetric or transitive. To be symmetric, if we have an element 1 2, it should imply uh, there is another element 2 1 in R. Let's see whether this is in this relation or not. We have no element 2 1 in R because 1 is not divisible by 2, right? Therefore, R cannot be symmetric. Similarly, if we check the transitivity, you will find R is not transitive. So the first question 1 is reflexive only. This is not symmetric nor transitive. Now the second question of question number 2. So R equal to xy belongs to A, y equal to x plus 1. The second element is equal to first element plus 1 in the set A, and A is given as 1 2 3 4 5 6. Now the relation R goes from A to A, or R goes from 1 2 3 4 5 6 to 1 2 3 4 5 6. So the elements of the relation will be in the form first element is 1 2, because y is equal to first element plus 1, 1 plus 1 2. Similarly 2 3, 3 4, 4 5, 5 6. But if we take x equal to 6, the y will be 7, but 7 is not in this set. Therefore R contains these elements only. So you can see here if R is reflexive, if it is asymmetric or transitive. Now, to be reflexive, the element in the form AA belongs to R, but here no AA elements belong. AA means elements like ARA. Here 1 2 2 3 3 4 4 5 5 6. No element in this form. Therefore R is not reflexive. But whether it is symmetric or not, let's check. To be symmetric, 1 2 elements should imply 2 1 element. Is there any element in the form 2 1? No. So this is not symmetric as well. Now, whether it is transitive or not. Suppose we are taking two elements 1 2 and 2 3, then according to definition of transitivity, it should imply another element 1 3. We have taken these two elements 1 2 2 3, so the third element will be 1 3, but there is no 1 3 in this relation R. Therefore the given relation is not symmetric, not reflexive, not transitive as well. So guys, are you enjoying the session? Because the topic, relation, function, these are very interesting, right? Relation is very interesting. So I think you are learning the relation symmetric, reflexive, transitive, and how to check a statement whether this relation is transitive, symmetric, reflexive, right? So let's proceed to the next question. Here the third question is R equal to ordered pair AB. AB belongs to Z. This Z means set of integers, and A plus B is even in the set of integers Z. You know very well the set of integers Z. Now R goes from this set to this set. We have to check either R is symmetric, reflexive, or transitive. Now here I have given some elements in R in such a way that this is enough to check the symmetric, reflexive, and transitivity. I have taken these elements are equal to -1, -1. So -1 belongs to Z, -1 plus 1, -2, -2, -3, -3, and the two elements -1, 5, 5, and -1. The set of integers. For any element in the set of integers, we have the element in this form AA. That means -1, -1. Similarly, we can have -2, -2, -3, -3, or +1, +1, +2, +2. So the relation R in the set of integers, it is obviously reflexive, right? This is reflexive. Now for symmetricity. So here if I take the element -1, 5, so there is always 5, -1 in this relation on this set of integers. 5 is also an integer, -1 also an integer, -1, 5 integers. So this is reflexive also. Now we have to check either this is transitive. Now for transitivity, we have to take two elements in this R, and then these two elements should imply another element in this relation. If we satisfy this condition, then R will be transitive. So let's check. This is very beautiful. See here, the elements -1, 5, and its another element 5, -1. Now if two elements AB and BC belongs to a relation, then it should imply the another element AC, right? Suppose this is AB, BC. So the third element should be in the form -1, -1, which is this one, right? So -1, 5 and the element 5, -1 implies the element -1 and -1. So this is transitive also. You can check all these symmetric, reflexive, transitive for other elements also. I have only taken a few elements. So the relation R is symmetric, reflexive, and transitive. The next one is R equal to ordered pair X, Y such that XY belongs to A and X and Y work at the same place. Sorry, let's say A is the set of all employees in ASAB. I have not mentioned, but I am writing now. here the set A is set of all employees in ASEB, right? Now this is very obvious, this is very obvious. So I have not written down the solution, but I'm going to explain it. Relation R is in the way that XY belongs to this set. That means X and Y are employees. And the relation is defined as X and Y work at the same place. They both work at the same place. Now to check reflexive. This is very obvious that R is a reflexive relation, because if we take X comma X, X is an employee of ASEB, so we can have XX, YY, or we have elements in the form. So R is obviously reflexive. For symmetricity, if we take XY, then I can also take it as YX. Y is an employee, X is an employee. I am just interchanging it, right? So this is also symmetric. For transitivity, this is obvious. If we take XY, then the other pair is like YX. Then we have XX. So X is R is transitive also. So this is very obvious. R is reflexive, symmetric, and transitive. So I have not written down the solution. I think you are getting it. Now, question number 3. Give an example of a relation which is reflexive but neither symmetric nor transitive. This is also a very, very beautiful question, because which I have discussed already in the question 1 and 2. We have such relations, reflexive but neither symmetric nor transitive. So it is not too difficult to find because we have already. Let's see question number 2, first statement. The first statement of question number 2 is reflexive but neither symmetric nor transitive. Let's go back to the previous one. And here it is. The question was R equal to XY, XY belongs to a set A, Y is divisible by X in the set A equal to 1, 2, 3, 4, 5, 6, 7, 8. Now we have the elements in R, like these are the elements. I have already discussed with you, so again I am not going to repeat, right? Here we have concluded that R is reflexive for all elements in A. So this relation is reflexive and but neither symmetric nor transitive. So the example will be R equal to XY such that XY belongs to A, Y is divisible by X in the set A, right? The second question is transitive but neither reflexive nor symmetric. There are so many examples which will be transitive but neither reflexive nor symmetric. You can take any one of them, but I have taken a simple one, which is we define a binary relation R on a set 2, 3, 5. The set is 2, 3, 5 in such a way that R contains the element 2, 3, 3, 5 and 2, 5. So you can see here the elements 2, 3 and 3, 5 implies the other element 2, 5. 2, 3, 3, 5 implies another element 2, 5, which is in this relation. So this is obviously transitive. this is not reflexive because if this element 2 3 implies the element 3 2, no. Similarly 3 5 not implies 5 3. So this is not reflexive, and this is not symmetric also, because we have no elements in the form A relates to A in this relation. Therefore, this is an example of transitive relation, but neither reflexive nor symmetric. Now, this question, that means we have to find an example of a relation that is symmetric and transitive but not reflexive. So let's see. Given a binary relation on the set A 1 2 3 in such a way that R contains the element 1 1 2 2 1 2 2 1. So R contains these elements. Now these elements satisfy this symmetric and transitive relation. So for symmetricity, 1 2 stands for 2 1. So this is symmetric, right? Now transitive. For transitivity, we take the elements. Let's take two elements 1 2 and 2 1. Then it should imply the third one in the form 1 1. 1 2 2 1 implies 1 1, which is in this relation. So this is transitive also. This is not reflexive because we have elements 1 2 3 in the set A, but in the relation we have only 1 1 2 2, but there is no 3 3. For reflexivity, the elements should satisfy the definition of reflexive relation for all the elements in the set, but we are not given 3 3 element in this relation, so this is not reflexive. Therefore, 3 it is an example of symmetric and transitivity relation but not reflexive. The fourth one is symmetric and reflexive but not transitive. Now we have to find an example of symmetric and reflexive relation but not transitive. Let us take a set 1 2 3. Let us take B equal to 1 2 3. Now define a relation R. We are defining a relation R on this set B such that R contains the element 1 1 2 2 3 3 1 2 2 1 2 3 and 3 2. So this relation is symmetric because for the element 1 2 we have 2 1, and for the element 2 3 we have 3 2. So this relation is symmetric. For reflexivity, because we have elements 1 2 3 in this set B, we should have 1 1 2 2 and 3 3 in this relation R. Yes, already R has the elements 1 1 2 2 and 3 3, so R is reflexive also, but this is not transitive. How? The elements here 1 2, let us take these two elements 1 2 and 2 3. Let us take two elements 1 2 and 2 3. According to definition of transitivity, these two elements should imply another element 1 3, but there is no any element in the form 1 3 in this relation R, so this cannot be transitive. Therefore, it is an example of symmetric and reflexive relation but not transitive. Now the last question. it is the question: give examples of two relations such that one is an equivalence relation and the other is not. We have to find two examples of two relations in such a way that one is an equivalence relation but the other is not. So I am ending this session here. I will be discussing this question in the next class. So friends, if you are enjoying my class, then subscribe to my channel. So if you have any query, then do write in the comment section so that I can help it. And that's all about my this class part 3. So keep watching my videos. Till then, bye bye. Thank you.